Alright, so Logan wanted to hear about 2.5, number 7. So I'm supposed to consider a matrix A that has row 2 plus row, or sorry, row 1 plus row 2 is row 3, and show that this thing's not invertible. So by even asking this question, what is the tacit assumption here?
There are 3 rows.
Well, that it's not a zero matrix?
Okay, good. Yeah, it can't be the zero matrix because otherwise I wouldn't be asking if it's invertible.
Yeah. Also, like,
There's a, like a,
so because one of the rows is a combination of the other two, that's just proof enough that it's not invertible because they're linearly dependent.
good. So if I'm assuming that the rows being dependent is enough, right? I could pretty easily look at this and say, okay, well, look, dude, if row 1 plus row 2 is row 3, then the rows are linearly dependent, specifically with coefficients 1, 1, minus 1, and the rest can all be 0. Because I don't know how many rows this thing has. It has at least 3. Yeah, that would be kind of enough. I think they want, in this section, I don't know, like a more elementary version of that. Does this make sense? Like, that's pretty straightforward, right? The rows are dependent, we're done. That's not invertible. Like, there's no way this thing is going to be invertible. But they're asking some sort of more fundamental questions here. You guys see that? Okay, so I know it's not invertible, and now we've got questions A through C. A is a weird one. Explain why AX equals 0, 0, 1 can't have a solution. To me, that reads as they're assuming this thing has 3 rows. You guys see that? Because I'm even considering whether it's invertible or not, I'm going to assume this thing is square, too. You with me on that? Okay, so kind of cartoon-wise at the beginning, I'm thinking, all right, A is a matrix. It's got a vector row 1. It's got a vector row 2. And then this third row is row 2. I don't know why I keep reversing the order when I say this. Row 1 plus row 2. Guys with me on that? Okay, and then they're asking me to kind of consider this equation where I'm taking my matrix A, multiplying by a vector, sure, yeah, let's just assume it's a vector x, y, z, right? We'll just put arbitrary coordinates in here. And we're going to say that this is then supposed to equal this vector 0, 0, 1. It's all kind of with me on that? Okay. Just for kicks here, I'm going to just kind of call this vector x. The reason I'm going to call that vector x is, why can't this have a solution? What the hell do they mean add equation 1 and equation 2? What are they on about?
I think that what it is something where you take the dot product of row 1 and vector x and the dot product of row 2 and vector x. They both equal 1. So that
Wait, they both equal 1?
Or no, they both equal 0, sorry.
Okay.
And then the third row would obviously have to be the dot product of row 1 times x plus row 2 times x. And then that would insinuate 0 plus 0 is equal to 1, which it's not.
Good. Did you guys all follow that reasoning?
Yeah.
So when I'm doing this multiplication, right, I pick my vector x, twist, drop on. So I'm getting row 1 dot x is 0, row 2 dot x is 0. And that third equation says row 1 plus row 2 in parentheses, dotted with x, should give me 1. On the kind of other hand, row 1 dotted with x plus row 2 dotted with x is 0 plus 0. And these guys should be equal, right? How do I know that? Yeah, but how do I know that I can like distribute a dot product through?
Because there's a theorem for it, or like a proof.
Yeah, this is the level of thing I'm kind of expecting you to know basically where it is in the book, or know that it is in the book, right? So, yes, we can distribute dot products across addition, and one of the places, or one of the justifications that you could use for that is, it's in the vector section in the textbook, right? Like, it's someplace in chapter 1, probably in 1.2-ish. Another way you could know this is you could say, well, the dot product is just multiplication by a transpose, right? And you could say, okay, and matrix multiplication has this property. Another way you could do this is you could pull out elements, right? And say, okay, so row 1 is actually made of some letters.
Yeah, that's usually my approach.
Row 2 is made of some different letters. And then row 1 plus row 2 is made out of the sum of those letters. You could follow this back to distribution of real numbers too. You guys see that?
Yeah, for this question, I just picked a sample A, with number 1, 2, 3, 4, 5, 6, 7, 8, 9.
Ah,
and one
don't
paragraph.
do that. That's a thing that students do a lot. It's a thing that you'll see me do sometimes when I'm like investigating. It does not amount to proof. So if you're putting numbers in here, you may just get lucky. It doesn't make a proof. It can, if you're having trouble proving something, it can provide you with some insight. Does that make sense? So you'll see me do it occasionally, like if I'm puzzling my way through something, I'll fill a matrix with numbers and then play with them. But rightly, they should be variables, unless I know something. That all make sense? One of the kind of reasonings for that is you might think things like, well, I mean, my favorite one is like, don't pick 2 for anything. It's like, if you pick the number 2, all of these operations give you the same output. And you might be like, why are those different symbols? Right? That same kind of shit can happen with matrices if you just get a little unlucky. And human beings have a tendency to pick the same, like, 8 random numbers. Like, you're not a good random number generator, so don't count on it for much. So that was why we can't have a solution, right?
Yeah.
Okay, and then which sides might allow a solution? So that'd be me reframing this question as if there's a B1, B2, B3 in here. What am I gonna need to have happen?
B3 is going to have to be the sum of B1, B2.
Yeah, you guys see that? So if I'm gonna have a solution, my vector looks like this. You guys with me on that? Okay, just because we're gonna kind of get into this a little bit later, vectors like this are the range. You guys see that? So I'm only going to be able to solve this if the vector on the right hand side is in the range of my matrix A. Arbitrary vectors B1, B2, B3, those are things in the codomain. And in this case, the codomain is strictly bigger. You guys see that? The codomain is all of R3, but I can only solve things like this, and this is a 2-dimensional z-plane. You guys see that? Ish? Okay. To make that really explicit, these guys look like B1, 0, B1 plus 0, B2, B2, right? You guys with me on that? Okay, and then if I pull the B1s out of each of those, that's B1 times the vector 1, 0, 1, and B2 times the vector 0, 1, 1. You guys see that? So the range of my matrix A, this guy, is any vector in three-dimensional space that I can write like this. You see that? And these two vectors are just two vectors in the plane, right? Cool. And then, just to quickly answer C here, if we eliminate, what happens to that third equation?
It becomes, row zeros.
Yeah, I get a row of zeros and equals whatever you have in the B3 spot. So either a number or 0. In the case of 0, you can solve this. In the case of a number, you can't. Cool?